Representing molecules, sections 2.1 and 2.2. You notice in section 2.1 that we're trying to find the patterns that exist between molecules that have similar smells. Notice for a minty smell, vials 1 and 4, they both end with one oxygen atom and their names end in O-N-E. For vials 2 and 3, the fact that they're sweet is given away by their name endings, ATE, as well as the fact that they each have 2 oxygens in their molecule. Finally, fishy is a smell all by itself with an N, nitrogen, in the molecule formula and an amine in the ending to the name. Let's use these to help us predict the smells. So what do we know already? Methyl octanoate. So the fact that there is this ATE ending, we can go back to the previous page and see along with the 2 oxygen atoms that this is probably going to be what smell. If you guessed sweet, you're right. If we look at the second one, monoethylamine, notice the amine ending as well as the nitrogen. We know from the previous slide that the smell must be fishy. Ethyl acetate, again we encounter the ACT ending as well as the 2 oxygens in the molecular formula. Again, like the first one, this tells us that we probably have a sweet smelling molecule. Alright, so far so good. Let's go to section 2.2. What is a structural formula? As you recall, when you have just a listing of the number of atoms of each element, that is called a molecular formula. However, that doesn't always give us enough information. A structural formula such as this one or this one tells us that these atoms are arranged in a specific pattern or in a specific order. So when we look at these, we can tell, for example, these 2 molecules, that even though they have the same molecular formula, their atoms are bonded together differently. And you can get a huge difference between ethyl butyrate, which happens to be a sweet-smelling pineapple, versus just by rearranging it, you get hexanoic acid, which smells like gym socks. Yuck. So, molecular formulas, structural formulas, and isomers. Let's review. Say you have this structural formula on the left. What would be the molecular formula? If you're asked this question, all you need to do is realize a molecular formula is just listing the number of atoms of each element. So, how many carbons do you have? 2. How many hydrogens do you have? 4. And how many oxygens? 2. An isomer of this molecule would be to go ahead and draw a structural formula similar to this one with the same number of carbons, hydrogens, and oxygens, only bonded differently. So let's see if we can do that. I think what I'll do is take this oxygen right here, take it out, and put it in between the carbon and hydrogen. If I do that, I'll still use the same atoms, but I'm simply bonding them differently. So we would say this is an isomer of the structure on the left.